Hello and welcome to the start of Chapter 6. This entire chapter is all about on electrons, the electronic structure of the atom. So really where electrons exist on each individual atom and how that changes the properties of those atoms and why it's important in chemistry. So um, this next few slides will be just upon the properties of light because electrons and photons have similar properties and also interact. So, starting with light, um, experiments with light have shown that light has two what were originally considered mutually exclusive properties. And the first property I'm going to talk about is that of waves. So light it is known from a certain type of experiment called an interferometer that light has a wave property. And so if you shine a light on a object, it has a barrier, essentially just small slits in it. What you will get from that light is an interference pattern. And we know from classical physics and experimentation, the only place that we get interference patterns like this, where we'll have certain places where the wave will show up and certain places where it won't, so it's not showing up here, but is showing up here, and so on and so forth, is from wave properties for sound waves and for waves in springs and things like that. And so it's been known for a while that light has wave properties. Experiments show that light is definitely a wave. The odd thing is that light is also a particle. And this seems really, really counterintuitive because things that are waves are not particles, and things that are particles that are not waves in our everyday experiences. But light has properties of both. We know light is a particle because we can get light radiation to shine into a conductor onto a metal surface, and we know that we can get excitation of electrons in that metal surface. And if light weren't a particle, it would not be able to transfer energy the way that it does in order to excite these electrons. And so it's been shown through an experiment such as this, where you have this metal surface and you're shining certain wavelengths of light onto this metal surface. We will essentially get an excitation of an electron, and that electron will spring free from the metal surface and will go to a positive terminal, and we'll actually see a current running through this sort of thing because of what's called the photoelectric effect. And this is an effect that would only happen if light has particle properties. Since light has waves, all waves have two fundamental characteristics of them. They have a wavelength, that is how long an individual wave or how large an individual wave is, how much space it covers. So wavelength and frequency. And so what a wavelength is if you go back to your trigonometry, you'll remember from that there are these waves that were represented with sines and cosines. And the sine wave is represented here, showed up here, where you have essentially, this one's showing a wavelength for a sine wave. So if you start at any given point on a sine wave, go through the motion or the revolution that completes the sine wave, where it starts over and repeats itself. See how that's a repeating pattern of this first bit? Start from that to where it starts, and then to where it starts repeating. That entire space or length is what's called a wavelength. But for waves that are actually moving, so this is for a static thing, not necessarily for a static thing, but works for a static thing, that any sine wave shown actually has a wavelength. But these waves are always in motion, and so since they're in motion, there's some time that any given portion of that wave will go through that entire wave revolution. And so if you pick a point on this wave, and as it's moving through, it'll go through that revolution. Well, that's called a frequency, except it goes from one peak to the next peak. So if we start here, go for see how long it takes this point to get from here, go down and back up to here. That takes a certain amount of time, and that time is how much it takes per second. So this is on a per second basis. So wavelength is the distance between the peaks, and frequency is the time it takes for that particular wave to cycle. So since it's in cycles, we have units of 1 over seconds. Remember, if you see this, you could read it as 1 over seconds, which is units of seconds to the -1, which is units of hertz. Okay, so seconds to the -1 is hertz. There's all kinds of corny jokes, and I'll try to keep them to a minimum as we discuss that. So one of the interesting things about light is that we know how fast any light particle moves, and this is the speed of light for light passing through a vacuum. Essentially, nothing getting interfering with it, and so speed of light c is equal to 2.9979 blah 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 times 10 to the 8th meters per second. That's very, very fast. That's actually considered to be a speed barrier where nothing in the universe can move faster than the speed of light. And there's a relationship between the speed of light, the frequency, and the wavelength for any given bit of light. So this relationship works for all different types, different colors of light. So the entire electromagnetic radiation spectrum, where the speed of light is equal to the wavelength times the frequency. So if you think about this, if you solve this for frequency or wavelength, you get c over lambda is equal to frequency. By the way, this is new. This is lambda. Just remember, this is wavelength and this is frequency, okay? So speed of light equals the wavelength times the frequency. So as the wavelength increases, the speed of light is a constant, right? We're divided by something bigger and bigger, which will make the frequency decrease. And if you want to rearrange this to solve for frequency, for wavelength, you get c over v, or nu, is equal to lambda. And so again, as this increases, the wavelength itself decreases. And so these are what are called inversely proportional. As frequency goes down, wavelength goes up, and vice versa. So the electromagnetic radiation spectrum contains all types of light that we know of. Light is just a common term for electromagnetic radiation and is mostly used for visible light, okay? But can be used for other forms of light. So as you notice here, the frequency, is increasing from right to left, and wavelength is increasing from left to right. And so, since these two are inversely proportional, this makes sense. And so, as we increase the wavelength, as we're moving across wavelength-wise, we are going closer to radio frequencies. So, the shortest wavelength light is gamma rays, the longest wavelength light is frequency, the fastest is radio frequencies. The fastest frequency light is gamma rays, and the slowest frequency light is radio frequencies or radio waves. So remember that these two things are inversely proportional, and this little sliver of light right here at these particular wavelengths and frequencies, those are what will make up our entire visible region. So from violet all the way up to red. Since light has particle effects, light particles themselves are what are considered quantized. That is, instead of being a continuous set of light, so that there's any frequency the light can have, it's actually got only certain frequencies that are allowed for any given bit of light. And these frequencies are governed by this little constant called Planck's constant. So light can only be multiples of Planck's constant, and that makes it have an effect that is called quantization. Instead of being continuous, it is quantized and can only be at certain levels. actually a relationship between the frequency of light and the energy of light, whereas frequency increases, the energy increases, and the frequency times this Planck's constant, this quantization constant, is equal to the energy of that light. Planck's constant is shown over here, where it's 6.626 times 10 to the negative 34 joules. This is a time symbol, so joules times seconds. That's the units of Planck's constant. So we can actually use this relationship here and multiply any frequency of light given by Planck's constant to actually calculate the energy for any. So one interesting question would be, which of these two has more energy? A photon of infrared light or ultraviolet light? And so the way to answer that is you would look and see, well, frequency is directly proportional to the energy. So if you look up here, infrared is over here. It's got a lower frequency, times 10 to the 13th times 10 to the 12th. Lower frequency than ultraviolet, which is up here, times 10 to the 16th. So ultraviolet light is more energetic, and that's why and this is actually the type of light that tends to damage skin cells and cause, certain types of skin problems.